Okay, YouTube, in this video we're going to talk about the relationship between two variables or two or more variables when we talk about direct variation and what is kind of meant by that. So when we talk about direct variation, it's probably the most common type of relationship that you see in, say, I don't know, like maybe a high school math class, but we often say that two variables that are related, we call them x and y. This could be like, you know, distance and time, or it could be time and temperature, but you know, more generally x and y. So we say that y varies directly with x if two things vary. We could say x varies directly with y, but when we read it this way, we basically mean that we have something of the following form: y equals k times x. So the first thing we want to note here is this variable k, or sorry, not variable, I guess we could call it value k. It'll have a value. We call this the constant of variation. And so anything that's directly varying, we would say that y and x here, there's just some value that we tend to say is in front of x, and it would modify the relationship that these two things have with one another. So these would be some examples of y varying directly with x. We say we identify the constant of variation as being the coefficient of x, which is our k value. This should say y equals 2x here, as a matter of fact, but we would say that our k value here would be 2. 2 would be our constant of variation. We say that y varies directly with x. Here we have y varying directly with x, but our k value is a third, so that changes their relationship. We could have a k value of pi or a k value of -4, but in any of these instances, what I want the audience to basically notice is that when we say that two things are varying directly, and I can tell you this, more generally speaking, we say that if you were to say two things are varying, they're on opposite sides of the equation, typically listed that way, and they're on the same level. And what I mean by the same level is that they're both in the numerator or they're both in the denominator. So if we were to, you know, reciprocate both sides here, we would say that this would be another way to write, you know, x and y varying directly because they are on the same level as one another. It's just that we tend to write it as y equals kx, and they're all over 1. So let's look at a couple of relationships down here. Actually, I copied and pasted from this, it seems. So this should be y equals 2x, and I'll rewrite this here. So, and we have y equals 1/3 x. What I want to do is I want to learn about the type of relationship that two variables have when they vary directly. And basically, we can do this pretty quickly just by stating the fact that anything that varies directly, you're going to say, is of the form y equals kx. Well, then this really is just a linear function. So I'm going to fill in some values here. How about -2, -1, 0, 1? And we say, well, if I plugged in -2, I get y equals -2 times 2, which is -4. Whereas if I plug in now, you know, -1, we get y equals 2 times -1, which is -2. And we plug in 0, we get 0, and we get 2. You can see that as x is going up by 1 every time, we can identify that this is direct variation, because as x is getting bigger and bigger and bigger, what we can see here is that we're observing that y is getting bigger and bigger and bigger. So one big thing that gives away direct variation is that grows linear growth. Here we have linear growth, and as x gets bigger and bigger, y gets bigger and bigger. And another way to represent this, of course, is graphically. We would say at -2, we're at a height of -4. And at -1, we're at a height of -2 here. Actually, -2 would be, let's fix that. -2 would be right there if I'm calling that -2, and we say 0, and then 1, we're at 2. And so we get this line, this linear function here, and this is y equals 2x. Okay, so all this being said, we can tell direct variation if y and x are on opposite sides and they're on the same level, and we can see this by the linear growth. So again here, if I were going to plug in convenient values, like maybe -3, 0, 3, and 6, just because I'm multiplying by a third times -3, they're reciprocals, so I get 1, and it'd be negative. And anything times 0 is 0, and I would get, you know, 3 times a third here is 1, and 6 times a third is 2. Again, this would be direct variation, because as this goes up every time, as our x value variable goes up every time, so does our y value variable. It's just going up by a factor, well, a difference of 1 every time. So what we're going to do is we're going to look at really quickly here this. We say sometimes you'll see direct variation listed thusly, and I just want to be clear on the fact that y over x equals 2 is still direct variation, because we could readjust this by taking both sides of this equation times the x, and we would get the x's to cancel here on the left, and we get y equals 2x. So that's really just the model that we see right here. So what we're going to do really quickly here is we're going to throw together a couple of variable relationships, one more generally and one more word problemy, and then find some unknown values using our model. Okay, so we say y varies directly with x. This is our first clue that we could write a model here. When we say y varies directly with x, we say y and x are on opposite sides here, and they're on the same level. That is, they're both in the numerator in this case, and we say that there's a constant of variation. So here is our direct variation here. What we want to do is basically this. We say when x equals 2, y equals 6. What we're saying is we already have a data point here. And I'm going to make a table. I'm already thinking ahead here. Whoops. We say when x is 2, y is 6. So if we're going to use this model here, our first question is, well, if I want to know how they relate to one another, I know as x is getting bigger and bigger, y would get bigger and bigger. So what would our k value here be? What would be the constant of variation that causes it to do it in this fashion? So what we're going to do is we're going to substitute in this 2 comma 6 into this variable relationship here, and we get y equals k times x, where our x value is 2 when our y value is 6. So we get that, it follows that k is equal to 3 here. And so now that we have this, we're going to write a model. So the model is really just our direct variation, where now we know what the relationship is between x and y. We know that the k value must be 3. So this model would tell us what's going to happen to x as y does its thing, and vice versa, what happens to y as x does its thing. So now that we have this model, we've written the model here, what we want to do is use that equation to find y when x equals 7. So for instance, now I could say, well, when x equals 7, what is our y value here? And we can say, well, then y would be 3 times 7, which is 21, if these are varying directly. So on example number 2 here, we're going to do this with a word problem. I'm going to kind of take you through how you might do this, but it says the pressure of a gas varies directly as the temperature, or with the temperature. The first thing I want to indicate here, what are our variables? So we have pressure of our gas and temperature, and they vary directly. So if I can use whatever letters I want, instead of y and x, maybe I'll do this. I'll say pressure varies directly with temperature, so KT. So we have like y equals kx kind of form here. And it says if the pressure, now I'm going to write a little table over here. We say pressure and temperature. We say if the pressure is 12.5 atmospheres at a temperature of 250 degrees Kelvin, then what I want to know is, what is the pressure at a temperature of 350 degrees Kelvin? So I could tell you this. I could fill in a 350 here and go plug it in and work backwards to find P, but the thing here we're always going to need to find first is, well, let's find the constant of variation first. So what we'll do is we'll plug in 12.5 atmospheres, which is a pressure value, in for P. We'll go ahead and do that. We say 12.5 is equal to K times the temperature, and that was 250 degrees Kelvin. So I'm going to go ahead and divide both sides here by 250, and what I get is this. We get K is equal to 12.5 over 250. We could even get a decimal if we cared to do so, and I do care to do so. We say divided by 250, and so we get 0.05. So our model here is that the pressure is 0.05 the temperature, or 0.5 I think. No, we got 0.05, so I need to fix that. So we say 0.05 times the temperature. So now all we need to do is say, well, now that I know this temperature is 350, what's the pressure going to be? And we say, well, pressure would be equal to our constant of variation, which in this case is 0.05, times the temperature of 350, or 5% of 350. So I'll take that 0.05 times 350, and I get 17.5. So we would say that the pressure would be 17.5 if the temperature is 350, and these things vary directly. So that's more about the direct variation. The next video we'll talk about inverse variation. Cheers.